All right. So some of you might wonder why I rarely wear a shirt in my videos, and I started out doing it early on. In the beginning, they say we were monkeys, monkeys in the wild. Well, I say we're not much different than monkeys today. We haven't really come that far. We're still monkeying around. But monkeys working together can do some cool stuff, can have cool personality. When they're not, they're kind of pretty nasty. People are much like that. We're just like monkeys in so many ways. And so, like monkeys, we stumble, but we're smarter than monkeys. But we're like an evolution of monkeys, which is why it makes sense that we would be part monkey, because it seems to come out a lot. For example, we're looking up at the stars and we see an object go by, and all of a sudden, us monkeys, what do? Okay, well, we have some problems. For one, our technical view of gravity is flawed. Now, I'll tell you these things, and you can verify them on your own and find out they are, in fact, facts on your own. But Einstein and Tesla had competing theories about what made the universe operate. Tesla at one point claimed that he had a working model of the universe, not quite, but that he had a working model of the solar system encased in a sphere that was electrically charged to withstand filling it with other spheres that were also charged so that they would be suspended. Well, I knew enough about the electricity to know that was possible. I knew enough about electromagnetism to know that that was possible, but that implied certain things. If you wanted to assign a value to how strong the magnetism was, you would have to build this model and to have it operate correctly. And what he had done was figure out that he could place small spheres in this that were basically a negative magnet, for example, on the inside, and a sphere, pretty much. Didn't have to be, though. And then, but it is. And then another one on the outside that is positive, making both magnets bipolar, which is what the planets are. Only one is stronger than the other. So they have both attraction and repulsion. And that's the trick most people don't get about gravity. It's a complex thing because, electromagnetically speaking, objects can have attraction and repulsion. Well, according to gravity, they can have the same. And if you don't think so, try skipping off the atmosphere when you're trying to come in and tell me it doesn't work that way. Things can happen when you're at certain points. Now, Mars doesn't really have much of an atmosphere, and we don't expect that when this object would come close to, say, its atmosphere, that it would skip off. I don't think it came that close. I mean, it was still pretty far from Mars. But here's the problem. Early in Einstein's career, he, Tesla, and pretty much everybody else were in agreement that gravity was technically a weak force, originally identified as a law that would apply on Earth. See, that's Newton. The apple falling, well, that says we're on a big heavy rock. And the only reason this apple doesn't just hover is because it has weight. Okay, well, that's true. It's got weight, but also that the fact that we're standing on this rock means there's weight. And if we were in space, this apple would have no weight. Okay, well, that turned out to be true, guys. Pretty astounding stuff. Some of these people were incredibly brilliant. I don't claim to be all of them. Yet I have studied all their works and understand the pertinent information that's going on here. And what's made me do a video, guys, and wanted to make me bring a little light was the fact that I'm seeing so much bullshit on it. So allow me to explain. Our early 1900s, we had Tesla and Einstein basically both putting together theories of how the universe worked, because we all want to know. The problem is, Einstein predicted that it would be gravity-based, that all of the major functioning of the universe that we see would depend on gravity. But we can clearly see that's not true. For example, the sun is our biggest body. Okay, you might think that. Well, we have this thing called Jupiter. Check that out. It's pretty big too. Now, the sun is technically bigger, sure. Compare the two. And if you think that their spatial relationship is determined by their gravity, which is what the standard theory would say, it ignores electromagnetism. Only we know enough now to know that plays a huge part as well. The composition of these materials will determine their electromagnetism. For example, if Mars has a lot of magnetic materials in it that are negatively charged, which is actually kind of rare, but if that's the case, or this meteorite does, and the other does, both have positive, they would tend to push away from each other when their two fields interact. And that's going to be a measurable phenomenon. Therefore, if you were looking from another perspective, it could pass by something small in space that we didn't even see because it's so small, but it's a strong little piece of lodestone floating around in the universe that's dark and we didn't notice. And that interacts with that magnetic field and pushes it aside. But what we see is an orbit happening. Now, everything that we can tell, all these planets have an electromagnetic field. Earth does, it's bipolar. We know that. And that's the problem. This is a big electromagnetic field, guys. We have something called the magnetosphere. And if you guys look that up, you'll find out how big and intense that field really is. It's not a joke. We are hugely magnetic. Check a compass and see how that works. Here's the thing. The standard model really doesn't account for that. And if we're trying to program a computer with a predictive model of the universe, which is what we've done. We put all our physics into this model, and then it's supposed to predict how these objects move through the universe. The problem is there are big holes in our knowledge, and we don't put the pieces together. So that needs to happen. But for that to happen, the knowledge blanks need to be filled in. Now, during a conversation I had with some very smart people several years ago, some of them from NASA, we talked about the fact that we need to redefine the model. And they said, well, how do you want to do that? How do we go about that? And I said, well, first we need to find out how much of this is electromagnetic. That'll tell us how much of the rest is gravity. Because it goes both ways. There are forces there on both counts, and we can prove that. So accounting for those becomes a thing. Now, in the old days, which is why I brought you back to 1910 to start with, they had this big kind of argument that got quite political in terms of them being in a popularity contest between the two of them and not liking each other very much, which Einstein won. He was the hero boy. He was well liked by the media, and his theories were believed. The problem is, if you actually read his early work on gravity, he specifically stated that it was a weak force and it would encompass a short ring around the planet. Later, to compete with Tesla, he pushed that ring out significantly and decided that Tesla was partly right, that there had to be something else, and said it had to be more gravity. Brilliant guy, right? Truth is, when it came to particle physics, Einstein was the most brilliant guy I've ever read of anybody, and I've studied them all, and that guy was brilliant beyond anybody. We owe him so much in particle physics, man, you have no idea. But when it comes to space, Einstein had a lot more going for him. Hell no. That was Tesla's department. He studied electricity big time, more than Einstein did individually. Einstein studied the physics. Tesla, builder. Electricity, weapons, engineering principles, designs, practical things that he could work with. Sorry about that. Roommates were coming in. The problem is, we have now a situation where we've understood that they were both right. They both had a really good point in their given area. And the problem is, we were trying to figure out how those two ends meet together at a time when we really didn't have the ability to look. So what I recommended was that we now have the technology to look at these things empirically and see if they're magnetic, and then observe them going through and see how they respond. But to do that, we need to know the composition, which is why we talk so much about the composition of these materials, because it's actually really important to how they interact with other planets in our solar system. And then, only then, can we see how much gravity really has a part in this and how much electromagnetism really has a part in this. But In this case with 3IATLAS, what we are seeing is that when it came through, it got close to Mars, but gravity didn't seem to have much to say about it, which is weird because it's a pretty heavy object. Well, that is explained simply by the fact that it has a high nickel composition with no iron. It's not magnetic. And it's a ball of ice. Also not magnetic. Sounds to me like it's made of a whole bunch of non-magnetic stuff. And so it doesn't have much magnetism going on. Mars, a very similar type of body. Look at the surface of Mars. I don't know what samples we've taken, but I don't see it having anywhere near as strong an electromagnetic field as Earth, especially with a non-active core. Earth has a molten core of rotating metal mass, which contains lodestone. We know that. And very strong metallic things that are also very strongly magnetic, that are built in our core, that are in the form of liquid stone, magma, that's rotating around in this big ball, which creates a rotating electromagnetic field that's very strong. But other planets also have an electromagnetic field, which means we'd have had one anyway. Ours is just supercharged. Mars's is not. And so, what we expect to see from both a magnetic perspective is it relatively passing by without much effect, because Mars has very limited pull in terms of its electromagnetic properties, and this object also being of similar characteristics. Now, it's not that if you don't take a nickel, you won't get a response from a magnet, but pure nickel, which is what this is looking at, it's very pure, which is surprising, really. That is a different thing. And if you look at that and say, okay, well, that's very magnetic or not, this is important because, did I lie to you? Is nickel magnetic? Find out. Don't take anybody's word for it. Think about it logically. That's what we have to do at this point. Don't listen to anybody's word for it. Guys, we need to find out. Is it magnetic? Is it not? And we know the answer because we know the composition, guys. So this is why composition is so important, because now we can assess, A, it's very massive and very heavy. Okay, it's giving off a lot of water, which means a lot of ice was there. And it wasn't ice that was deep frozen like everybody's suggesting, and it took a high... No, it was barely frozen, because space isn't really as cold as they make it out to be, and we know that empirically from things like this. Otherwise, their predictions would be right about when it heated up in the atmosphere. Also, there are varying forms water can be in, like smoke, that could be frozen in that state that it's hard to explain. They underheat and pressure and all kinds of things that can happen. And in certain environments, it can be very cold. Space seems to have varying regions. Go figure. But it was also known by astronauts that went out in spacesuits that it's not actually that cold outside, but the sun is close by, and the sun is really hot, and you're outside the atmosphere to protect you from it. Of course it is. But as you move out, it is colder, and we know that. But we don't really know how cold exactly. And that is part of the problem. There's a lot of guesswork here. And so accurately producing a model is difficult because we're not sure about so many of the quantified parts of this. Like, there's so many portals in this that could give us a window into exactly what's going on, and we need to list them. Those are the variables that matter. The electromagnetic qualities of Mars, the electromagnetic qualities of the object. We've studied Mars a lot, and we've studied this object enough to know both. That is the trick. And according to what we know, gravity says, well, this shouldn't be an issue. It should just bend because it went by Mars this close. Only it didn't. Well, that's not it having propulsion. That's not it making course corrections. That's just simply it passing by without interacting with Mars's electromagnetic field, because its actual gravity is a very small field around it, and it didn't get that close. It didn't get close enough to actually enter orbit. Not even close, guys. It wasn't anywhere near the atmosphere. How's it going to be affected by its gravity? It's weightless in space, guys. Let's keep that in mind. When you have a rotating body with an atmosphere, it's like a suction zone and it attracts things. But it has to be really close for that. And I will bet you that that's what gravity really is.